Today we're going to be talking about CFD modeling. We're going to be doing CFD performance modeling on air-cooled chillers. External flow is becoming more and more an issue. We've gotten pretty good at getting the heat out of the data center, and now we're trying to reject it to the atmosphere. I'm going to use some multimedia here. I'm going to use a combination of some presentation slides as well as showing you some CoolSim as well. In the interest of keeping you from being distracted, I'm going to snap my camera off for the presentation, and then I'll turn it back on at the end for questions and answers, okay? So with that, I'm just going to switch my camera off. All right. So a little bit about our company, Applied Math. Many of you may have heard of us or know us. We produce the CoolSim application. My background is mechanical engineering and electrical engineering both. I was a vice president of product management and development at both the Ansys Corporation and the Fluent Corporation. Prior to that, I was involved in high-performance computing at the Hewlett-Packard Corporation. So I'm both mechanical and electrical, originally working in the field of electronics packaging for computer-based systems. And then later on, of course, I was involved with the development of high-performance computing and the deployment. And today I'm doing care and feeding for high-performance computing in a data center. So kind of full circle in that sense. I started this company in 2008. So we're coming up on pretty quick here, 20 years of doing this. We are a partner of the Ansys Corporation, which is now Synopsys. They've been acquired, same technology. When I was there at Ansys, I was responsible for a variety of products. Here, we really are a value-added partner. We take that Ansys general purpose CFD software and we build an application-specific interface for it so that it's easy to use, really easy to use, easy to set up, easy to run, specific to data centers. It is a SaaS model that we use for CoolSim. SaaS is software as a service. So it is hosted. The mesh solve post is all done on a cluster on your behalf. This saves you money. This is a cost-effective approach that I helped to pioneer back in early 2000s. We are experts in CFD modeling. We can do it all. If you're interested in doing anything that's outside of the typical kind of analysis that you see here today, we can certainly do it for you, okay? So our objectives today are to really just understand chiller fundamentals, review the airflow, heat rejection, understand how to model them, how to understand how to set it up in a CoolSim type application and run it, and how to look at the output. So we only have an hour, but in that hour, I'm going to cover quite a bit of material related to how these things work. I'm going to review a little bit of history with you in terms of thermodynamics. I'm going to stress your thermodynamics memory a little for those of you who have it. Let's start off with what a chiller is. This is an air-cooled chiller. You often see these, this is representative, by the way, of a lot of heat devices. You see these on rooftops. If you fly into a city or you look up at top, you'll find these structures everywhere. This is the heat rejection system for the building. It's often also used as a heat pump, bidirectional, but in our case, it's dumping to the atmosphere for data centers. They use these vertical V structures for heat dissipation. These are heat exchangers. The fan sits on top and pulls air up through these heat exchangers into the atmosphere. So it's pulling from the sides, and it pulls on this side, it pulls on all sides, and then up and out. Each one of these fans is pulling air straight up out. The number of fans is correlated to the amount of heat this device is dumping. The size of this device will vary depending upon its capacity. They typically range from 100 to 500 tons. They've got a compressor in it. They've got condenser coils. That's what these are. These are condensers. They're dumping heat. They have axial fans. Remember that when you're rejecting heat, you have to not only dump the cooling load, but you've got to dump the heat caused by the compressor and the fan. Remember that all energy delivered gets dumped to the atmosphere at some point. So if you've got a fan running, it's going to dump the power related to driving the fan and the compressor. Size is important. You can note the size here. These things range in size. This one is right now in inches, 342 inches long, 108, 101 high, deep, 93 high. The reason I point this out is that when we're modeling it, we're going to be interested in what the average inlet temperature is. These devices, their performance is correlated to average inlet temp, and that is something that you're going to want to calculate using CFD. And essentially, you want that at the midplane. You're trying to figure out what the approximate inlet temperature is right about at the middle of that chiller, okay? So average inlet temp is quite important because that drives performance. You'll see why in a moment. But keep in mind these numbers. Look at your build out, look at your spec sheet for the device, size this appropriately. I'll come back to this later, but I just wanted to point that out right now. So a little bit about how these things work. I'm going to do just a little bit here to remind you how these devices work. So you've got your data centers over here. You know, this is the internal representation of a data center. You've got thermal load in there being dumped. It comes out into a evaporator. Here's the evaporator sitting here. So this is where the heat is exchanged, and the cool fluid, generally in the form of water, goes back out, loops around, comes around like this. So that's one loop. The other side is gas. So here what we're doing is using a gas, and we compress it up so it absorbs the heat, gets compressed, and then it turns, of course, because of the ideal gas law, temperature rises. You get a very high temperature up here. You also get high pressure. These heat exchangers that I was showing you just a moment ago dump to the atmosphere, throwing the heat into the atmosphere, and then it comes back around and goes through, it's a phase change in there, goes through this mixing device, throttle device, evaporator valve, and then back. So you've got ideal gas running over here, some kind of gas, and over here you've got liquid. If you look at it from a thermodynamics point of view, this is a temperature entropy chart. Many of you may remember this from thermodynamics if you remember that far back or have seen it. But this is the temperature entropy diagram. The most important is here 1 to 2. In my mind, work, shaft work. You see it on the right, on the left-hand side, work in. I'm compressing a medium gas to get it hot so I can dump it to the atmosphere. So the temperature here, T2, it's got to be high enough so that I can dump. So if the outdoor air temperature is 110 degrees, I've got to lift, they call it lift, and the lift comes from this pressure right here. It's causing, from 0.1 to 0.2, I've got to put shaft power into that device in order to lift or pressurize high enough such that T2 is high enough above ambient so I can dump it to the atmosphere. Very critical, because if this atmospheric temperature is high, this lift will go way up. And if the lift goes up, of course, pressure and lift are synonymous. And what happens is you'll trip that chiller. Its performance will degrade. It only has a certain amount of pressure that it can provide before it starts having problems. And its performance will degrade as this point number 2 gets high. You know, as you go up in pressure, these things will start to have problems. So we compress up and then we come down. This is phase change. So we're going through isothermal change here, phase, because I'm using phase change to absorb that heat, or eject it in this case. Then I drop down. It's actually, this is the ideal path here in the dotted line, actually some entropy growth. We won't go into entropy growth, but here I'm down on cold again. So now I'm going to dump the data center load that's coming out of the data center into that loop using the evaporator. So it gets hot, again, isothermal phase change, and then back up again. Same cycle you see in your refrigerator in your home. Same cycle you see in your heat pump in your home. This is the Rankine cycle, very well used, very well understood. No magic here. It takes mechanical shaft power to compress the ideal gas so you can dump it to the atmosphere. That's all I really wanted to show you. I simply wanted to make sure you were aware of that and understood the basic mechanics of how these things work. They all work the same. There is no magic really in any of these. This is just simply how it works. So let's go back to the real world. We have, you know, a chiller of a certain capacity. In the US, it's measured in tons. This is an old method. Generally, it's also kilowatts. That's a newer representation. In America, we mix our units. We use tons and inches of water, but we use kilowatts, so we mix our units. So We're going to assume we've got a 400-ton chiller running at 80% load. So we've got a heat rejection about 1,300 kilowatts. Remember to include your compressor power and fan power. Just make sure it's included in your number. That turns into, a certain number of fans. This will be defined by the device. You're going to get a 400-ton chiller. Turns out it's got 10 axial fans. Turns out they're blowing about 10,000 CFM each. This number will be defined by the manufacturer. This data will be from the cut sheet, the spec sheet that you get with the device. So you will know how much heat is being dumped by each device. Temperature rise on these devices, they generally run them in the range, they model them or predict them in the range of 10 to 15 degree F, delta T. Okay? So that's kind of how they work. The reason we're modeling them is because of recirculation, spacing, impact of wind, what happens if one's not working, performance, redundancy, failure scenarios. And it's really inlet temperatures that we're interested in because the performance of them, it may tell you in the spec sheet that it's 400 kilowatts capacity, but it's 400 kilowatts of capacity on a good day without the wind blowing. If it's a bad day and the wind's blowing, you got to derate that device. And the question becomes, how much do you have to derate it? The question you're trying to answer is, do I have enough cooling capacity to cool this data center or not? How many chillers do I need? And you can do mathematics, algebra. You can say, well, look, I've got, 400 kilowatts of total load, and so I should use two 400 kilowatt chillers. That gives me n+1, should be fine. And generally, that's okay. But as we continue to drive up the density of these data centers and try to do more and more, that rooftop gets crowded, or the space beside the building gets crowded. And when it gets crowded, you've got to space things closer together. When you start spacing chillers close together, and it can cause issues, as you will see. And those issues look like this. What happens is they recirculate. The chiller, I'll show you in a detailed example, starts to recirculate on itself. The air wraps around and the exhaust air gets drawn back into the intake air and performance declines. So this is a derating chart here that says, as inlet temperature rises, as recirculation percentage increases, so the amount of that's recirculating from exhaust to intake goes up, the performance of that device goes down. Now that curve looks fairly linear. It's not, but in this range it is, so that's not a bad curve to look at. And it turns into a situation where it's going to degrade approximately 1% per degree F. So here's chiller performance as a function of temperature. And you see here that the cooling capacity is declining as inlet temperature rises. So down here at 75, 80, on a day like that, it's fine. But these rooftops get hot. A lot of time these rooftops are black. They're emanating solar radiant heat right off the surface. I've been on rooftops measured with an infrared thermometer showing 165. And if that chiller is too close to the surface of that roof, it's going to be inhaling very hot surface temperature, and that doesn't include recirculation, which does happen. So chiller inlet will cause the cooling capacity of the entire environment to decline to the point where you can no longer cool that data center. And you have to, as a design engineer, you have to be aware of that. You have to know where the corner of your design is. The corner being worst case condition. What's the worst case condition that I need to design for so that I can ensure I have enough cooling capacity to meet the load in that room? And this equation, if you remember, sort of summarizes that, right? The heat is equal to the mass flow rate times the specific heat times delta T. Delta T is inlet outlet temp. This is the T2, T1. So here, I'm looking at atmospheric outside temp here, and this is inlet temp. So it's the delta T times the mass flow rate, which is defined by the fans, times the specific heat, which I've shown as a constant, which is not a constant, as it turns out, because as temperature rises, the density changes, this number will vary. And that's a nonlinear behavior that we can capture in CFD. So we can model this behavior quite accurately and quite easily with today's systems. And what we're trying to do, again, is predict the performance of the system using a tool to understand where we are in the whole scheme of things. Okay. So the way you do it is you use a tool like CoolSim. It's not the only one that does it. It just does it really well. And this one's a very cost-effective way to do it. We try to make it simple. You model the chiller. The way we do it is you model it as a simplified block. I'm going to show you that in a moment. We represent the fans as momentum sources with velocity. We apply the heat load and the volumetric mass flow to something we call an HDU. An HDU is a heat dissipating unit. Heat dissipating unit could be anything. It can be a chiller. It can be an evaporator. It can be any kind of device really that dumps heat to the atmosphere or dumps heat in general. You define the ambient boundary conditions. Here we're talking about, generally speaking, temperature of air, density of air. Density of air will vary by altitude, of course, so you want to get your altitude straight. Wind direction, wind velocity. Okay. You have to create what we call the bounding box. The bounding box is the environment around the building. It has to be large enough so that you can get the flows to settle out. Generally speaking, on the downward side, you need it to be 3 times the size of the building. On the windward side, you need it to be a couple times the size of the building. The chiller blocks are generally 13 feet, 8 feet by 7 feet. They're generally, it depends on the size, of course. The one we picked earlier was that size. You know, the number of fans is proportionate to the size of the unit you've chosen. Set the ambient air temperature. So setting these things up is fairly easy. And we have created in CoolSim a block for this. I'm going to show it to you in a moment. But this is what we call an HDU block. It is really a block with inlets and outlets on it that has a function in it that allows us to dump heat. It allows you to define the mass flow rates. So here, I hope you can see this GUI. I'll bring it up in a moment and show it to you. But here what we're assuming is we've got, as you can see, 12 inlets and outlets on this device. So this one doesn't have 10, it has 12. And we're also able to define the specifications for dumping the heat. We are putting it up off the surface. You see the bottom of the red right there. And it might be easiest now if I pop over and show you this thing a little closer and live. I'm going to pop over and show you this device a little bit closer. This is CoolSim. I'm going to take it to full screen so you can see it. And you see this surface right here is the surface that is that midplane I was talking to you about. This is where the inlets are going to be. Below it, we have, in this case, put some skirts around it because that's quite normal, is to have a permeable membrane around the perimeter of it. So this is what we call a baffle in CoolSim. This allows air to come through it. So you can see here, I've got this thing set at 60% open. They're not really 100% open. The open area on the surrounding mesh material at the bottom of these chillers has some percent area open. This one's set at 60. This allows us to put a little bit of flow impedance in the air coming in, which is realistic. This surface right here, the start Y value of this particular device is going to be equivalent to the midplane of that original structure I showed you earlier. We're looking at a slice. We want to see what the inlet temperatures are at the bottom of this device. This one is set to be probably about 45 inches off the surface of this block. The block in this case is the top of the building. Specifications here, you can put the whole load in there for this entire structure. So we're dumping 432 kilowatts. We're set the delta T at 11. The delta T will define the mass flow rate. So remember I showed you earlier, heat is equal to mass flow rate times specific heat times delta T. So you can define the heat load you want to dump. You can find the delta T that you're expecting it to operate at. It will therefore it'll set the mass flow rate, at least the initial condition. Remember, these are all initial conditions that you set up in the solve. These numbers will vary during the computation of the analysis because density is changing. Density changes due to temperature. So as the temperature changes, the density changes, the mass flow rate changes. These are initial boundary conditions that are set. These are expectations. These come from the spec sheet of the device. So this is a 432 kilowatt device. It has 12 fans on it. The aggregate flow rate on this device is 121,000 CFM altogether. So it's about 10,000 each. You got 12 of them. you're going to have a delta T of 11. Now, as you move that delta T up, the mass flow will go down. If you move the delta T down, mass flow will go up. So you can wiggle this number a little bit, make different runs on it to understand the effect of the delta T, but that's a fairly conservative number, 12, 15, 10,000 each, you know what the spec is on that. So that ends up being about 11 or 12. And that's how you set that. The nice thing about CoolSim is once you get one of these blocks set up with its skirt around it, you can group it and clone it. So you only have to do one of them, then you can literally what we call clone. There's a clone button here that allows you to group this structure with its skirt and then clone it two this way, then group these three, clone it one this way. I mean, laying this thing out is quick. You can even take this group of 6 right here and group it and clone it over to here. A lot of symmetry in a data center and a lot of symmetry typically outside. You all are design engineers, I'm assuming. So you understand the symmetry here is typical because it allows you to do plumbing more effectively and piping more effectively, etc. This particular design has a screen around it. You see it right here. This screen is not unusual. This is a louvered screen. They do this for beautification as much as anything else. It causes issues for flow, typically, but it's there. It's almost always there. So here we've got airflow coming through that at about 50%. In other words, it allows air through it, but it's not perfect. It has some flow impedance. That will cause issues in certain prevailing wind directions. For example, if the wind is from the left to right here, it's going to hit that screen, come up over the top of that lip, and cause low pressure on the backside. These devices already will have low pressure in the bottom because they've got fans pulling them up. So I'm going to show you shortly, there's low pressures being generated at the bottom of these devices caused by their inlet fans. Remember, these are 10,000 CFM a piece, and you've got 12 of them, and 12 times N. You've got a lot of low pressure down low. That's your enemy. The low pressure at the bottom is going to cause recirculation to occur. So let me put that aside for a moment. I think I covered most of these things. We're using square representations here. You notice that my structures are all rectilinear. In reality, these are round fans, and I think you know that. The reason we use rectilinear has to do with meshing. Meshing is the mechanism we use in CFD to calculate the equations of conservation of mass, momentum, and energy. So the way CFD works is we take this entire environment that I'm showing you here, defined by this box, and this is called the bounding box, and you can see airflow direction. So this one's got air flowing straight across it. And we break it up into a mesh. A mesh is you can think of it as a polygon. Here we're hex dominant, so it's a hex structure, polygon, three-dimensional. On every surface, we do differential equations to calculate conservation of mass, momentum, and energy. So it's the non-solid surface that we're calculating. And that mesh makes a difference in terms of computation time. If I were to make them round, the computation time would go up. So in CFD, we try to be conservative about or sensitive to computation time. And so rectilinear structures are often used instead of round structures to save time and to give you approximately the same answer. So all I did here is to show you how we do that. We preserve the cross-sectional area. So what you do is you say, well, you know, I've got 32-inch fans, 36-inch fans here. So I simply, in step 1, calculate the circular area, you know, pi r squared or pi times d, whatever. And then we take the square root of the area to come up with the size of the opening. So the opening here is 32 by 32 on a 36-inch round fan. Pretty straightforward. I simply showed you how to do this mathematically, or so in case you forgot. But a very common thing to do is to size those things to be a rectilinear equivalent. That still preserves the flow. It gives you the same mass flow rate. It gives you the same characteristics. It gives you the same pressure deltas. And, you know, the issue of the round corner versus the square corner is insignificant in the greater scheme of things, essentially. So, and then what you do is you set up your wind profile. You include nearby objects or structures. If there's stuff on the rooftop, you put it in as a block. If there's stuff on the ground that you think is going to be in the way, we generally do not model what's called ABL, atmospheric boundary layer. So in some studies in CFD, we do include atmospheric boundary layer. For example, there's a ground effect, right? Velocity is lower near the ground because there's friction on the ground. There's a boundary layer on the ground, and therefore you have a velocity profile that is different at the ground level than it is up off the earth. But we generally don't include it here because it's not that significant. We're only talking about buildings that are, 30, 40, 50 feet. The air is generally uniform up there. Let's put it another way. When we've used, velocity curves based on height, it doesn't change the output very much. It's kind of the same. So we don't generally use them, nor do we use temperature. Temperature is sometimes varied as a function of height as well. As you know, the upper atmosphere is colder than it is down on the ground. But in a building of 30, 40 feet, 50 feet, you're not going to get that much temperature delta. So they're there, and they can be used, but generally not a big effect. They're a second order at best. The wind direction comes from what we call the wind rose. If you've never seen a wind rose before, they look like this. I wanted to point it out to you quickly just to show you what they look like. You can generally find one for an airport near you. The software has links in it. CoolSim has links to places like National Renewable Energy Lab and the other places that have this kind of data. It's pretty easy to find on the web these days. You can use Google and find an airport near you that has a wind rose. They look like this. That's why they call it a rose. You see probability of wind here in these circles. Concentric circles are the probability of the wind. Colors are the magnitude. So you can see here I have a 2 to 4 mile an hour wind. A lot of the time I've got a wind that flows from the east. 6-7% of the time. I also have one that flows from the west. 5%, 4-5% of the time. My absolute magnitude, the biggest one is really in the range of 15 to 19 mile an hour wind coming from the west. I should check that one. That's one I should look at in my model. I should also take one from the east and take a look at that at 10 miles an hour. So what a wind rose does is it gives you an idea of what the prevailing winds are and how you should set up the wind so that it's blowing on your model. You want to try to represent the wind conditions you're going to see on the site. And then you run. So what I want to do is to show you some output here. CoolSim is quite nice in that it generates this hyperlinked output report. I'm going to show it to you. It gives you things like vectors and streamline plots and recirculation zones. So let's take a look at this run that we have. Now, the nice thing here about this is that it's fully automated hyperlink. Okay, and what we do is we give you an overall description. Now, this is the room is the bounding box, so you can see it's 500 by 500 by 100. And we're covering 250,000 square feet of volume of space, so to speak, not volume, it's area. We've got a temperature of 110 degrees. We've got a velocity of, it's in feet per minute. That ends up being about 30 miles an hour. Wind, flow angle 90 degrees to the device. And we also have these output reports here. These are the actual heat being dumped by each of the devices numerically. So we have it for all the devices. For the groupings of the devices. So here we have a delta T and a mass flow rate and amount of heat being dumped. So it reports it uniquely here. Over on the left, we have a little more interesting. We have the flow path lines. So let's take a look at what's going on with our system now that we've run it. And again, one of the nice things about CoolSim is you can share this information with one another. So here are my path lines, and what I'm going to do is take this URL and I'm going to copy it, and I'm going to go back to our little chat area here. And if you go to the chat, I'm going to paste this into the chat, and you're going to be able to view this on your own. So this is viewer gets to participate in the in the webinar from their own system. So if you go to chat and you hit that hyperlink, you'll be able to see what I see, and that's one of the nice things about CoolSim. So with your mouse, if you want to follow along, you can see here what's going on with this design. I've got wind now blowing directly from the left to the right in this image, and you can see that I've got recirculation going on. Now, one of the nice things about this viewer is if you point and you've got a right mouse, if you're not on a Mac, you've got a right mouse, you can hide a surface. So right mouse hide. So I just hid the surrounding screen, and using my arrow keys and my control key to manipulate this image so that you can see the recirculation. And you begin to see it. You see the air coming up and being sucked into the intakes of the downwind devices. And that's what's happening, is you're contaminating the downwind devices with air coming out of the exhaust of the upwind devices. You can even see it wrapping around the edges. It's just not in the linear direction. It's also horizontal. It's coming around this way. Having a 3D modeler like this and being able to manipulate an image on a screen provides tremendous visual perception. This is a human physiological issue or phenomena that if we can manipulate it and see it, we're able to understand much better what's going on. You see the exhaust temperatures here are even higher. Look, we're exhausting at 150 degrees here because the intakes are high, and I'm still doing a delta T. So this is a plot of temperature, and you can see here that by manipulating, you can see the problems I'm having. I'm straight wind in this case. All I've done is stack them up. Nothing unique. I don't have any obstructions in the way. The screen, I'll show you in a moment, is causing some issues. But that's kind of an interesting representation of what the problem is. Now, one of the other shots that's most important is what do those inlet temperatures look like? And we've got a plot of that right here. This one takes a second to load because there's a lot of surfaces on it. I'm also going to put this one in the chat so you can, and by the way, these will persist. So after the webinar, if you want to bookmark these things, you can keep them and look at them and show them to your friends. You can also view them on your phone, by the way, which for someone like me is just amazing, considering that when I was young, we used to carry the equipment with us on the planes to show this kind of stuff. But you can see what's happening. So the air is again coming from this direction. Those inlets aren't too bad up front. But as you move downwind, inlet temperatures start to rise. And that's going to cause a degradation in the cooling capacity of these devices. Again, about 1% per degree F. So you see the devices downwind here are running at about 6 degrees higher than the ones up at the front. So I've got about a 6-degree degradation and overall chill capacity of the units downwind. 6% is not that bad. I mean, this one probably is fine. However, it's not always fine, believe me, because we do a lot of these and those things get really high. If you start to get up into the 140-degree range, the compressors will actually trip and you'll have a high pressure condition and the chiller will shut down. And it can occur. I've seen it occur. It depends on how much density there is. Depends how many chillers there are. Depends on, as you'll see in a moment, is there auxiliary generators running, for example, that are adjacent to this system. But this is exactly what you're interested in. This is the most important shot right here, is the average chiller inlet temperature as a function of wind condition. Now we're only looking at one wind condition with one temperature. That's why you want something that runs fairly quickly and is fairly cost effective to use so that you can do multiple of these. CoolSim's quite a cost-effective, I would argue, the most cost-effective solution for doing this kind of thing. Run times on this run right here took me 30, 40 minutes to run. Doesn't take very long to run. And you can get some good insight about what's happening with your model. Okay, so let's go back to the presentation here. I think that was most of what I wanted to show you in the output. There are cut planes there too. Let me just show you one of those. So this is, there's a couple other things there I wanted to show you. So let's go back to that for a moment because there was also these cut planes. Let's take a look at pressure. I wanted to show you this pressure issue. So I'm going to show you a slice of pressure here and you'll see what's happening. Let me bring it around. And again, I'll share this one with you. But you see on that leading edge, we've got a low pressure area, right? I told you this would occur. So underneath these devices, the pressure is lower. This is relative pressure. I've got it in inches of water. It's relative the overall pressure in the domain. And you can see as you come over this edge, and I could tighten this range up a little bit and show you more vivid color here, but you can see it right now, even with the range I have. So what happens is the pressure starts to drop and we're quite low here. And that's not too bad right there because it's the leading edge. But as you go downstream, this again, low edge low pressure underneath is going to cause that recirculation to occur. So you can see it in pressure. There's a couple different pressure slices here that I have. This is another one that's kind of interesting. I'm slicing in the other direction. I'm looking at pressure as a function of color. And you can see the low pressure is being created underneath those devices that are going to be pulling the air in. So that air wants to naturally recirculate because it's got a low pressure underneath it. And these fans don't have a lot of momentum. They're 10,000 CFM, generally 10, 12,000 CFM each, but they don't have a lot of static pressure. They're just big axial fans. And so they don't really have a lot of juice. They don't have a lot of exit velocity. They don't have a lot of momentum. And that sometimes can cause issues. So I wanted to show you those as well. Yeah, all right. So the role is to model this stuff with multiple chiller banks. You generally need an extra one, understand failure scenarios, understand ambient studies, ambient conditions that can occur based on average temperatures seen in the geography you're looking at. Also looking at the wind profiles in the geography you're looking at. You want to integrate it with the data center airflow, but not a coupled solution. Some people ask us, well, can we do both the internal and external at the same time? That's not necessary, and it would be a big model, and it'd be redundant. Break them up into two. Do the internal first, understand what the loads are in the room, understand how much heat you're going to need to reject, and then build a separate model for exterior. Then use the output from the input model or the interior model to drive the output model. In other words, my total data center is going to be X gigawatts, whatever the number is of total load in the data center. That includes, by the way, the fans. Remember, fans are important. So you've got to include cooling the fans of the air handlers. You've got to include the compressors if there are any. You've got to include, of course, the loads of the individual racks. That's going to be the amount of heat you have to dump. Then use that as a baseline criteria for determining how many chillers you need and where they're going to be. So, and by the way, there's also auxiliary generators, right? More and more we're seeing data centers that use auxiliary generators in case of power failure. We're seeing more and more data centers that use auxiliary generators just to drive the data center. So what's happening in big hyperscale sites is we're seeing the deployment of turbines, gas turbines, sometimes diesel generators, but often gas turbines that are running on site generating power for the data center. And those things have hot exhaust. So here we are with heat again. Often they're 900, 1,000 degree Fahrenheit coming out of those gensets. And we need to know if the exhaust of those generators is getting entrained into the intake of the chillers. And this all relates to the fact that real estate is expensive. So you want to try to keep the size of the data center in terms of real estate, the area onto which it is developed, as tight as you possibly can. And so what I see designers doing a lot is stuffing this equipment very close together for economic reasons. I get why. However, you can run into some issues with the exhausts and training and ruining the environment. So here's one. We've got 51 chillers and 10 gensets per building. This is a fairly small one, 2 gigawatts of heat dissipation here. So this is a fairly small one. I wanted to show you this one in the modeler as well. See if I can pull that up. So here we have a bigger one. And at CoolSim today, you can model these fairly effectively. We do have a size limitation in terms of just sheer complexity. Sometimes we have to help you. We are a full service firm, so if this modeler can't do it itself, we will model it for you. Remember, this has got full Fluent behind it, so we can model anything. I've seen Fluent go to nearly 1 billion cells, so it can do it. It's just a question of, how hard is it to do it, and do you need our help to get it done? So now the generators over here are modeled as fairly simple devices. We're not really concerned about what's in it. These are diesel generators in this case. We've got some inlets and outlets. So this is the heat exchanger cooling the device here. So you've got some air going through it. This is the stack where the exhaust comes out. These are quite simple. You simply set the boundary condition of these inlets and outlets and put them on a block. Once you create one of these things, you can clone it. So you just group that and say, I want 4 more of them with an offset of X or Y or Z. And same thing for each structure. So you can lay out an entire structure like this one, and then clone the whole thing 2 times in the Z direction and be done. So laying it out in CoolSim is quite easy and quick, and it's designed to do it. You also notice that we've got chimneys on here. This is an idea that is used sometimes to help reduce the amount of recirculation around the device. So what you're doing is trying to channel that. You're trying to make a larger distance, essentially, between where the air is coming out and where the air is going in to discourage recirculation. So I see chimneys being used sometimes. Other techniques include putting a horizontal surface between these chillers so the air can't wrap down around it. These things are expensive. They do work. Airflow management exterior to the building is often the same as airflow management inside the building. You're trying to separate hot and cold and keep them from interfering with one another or mixing with one another. Not always easy to do, but that is what you do. And then you run the model on this. This one has a airflow going at an angle to it with a certain temperature and a certain velocity. And then you run the model to see what happens. And so here, I think I have a hyperlink. I guess I don't, but I can show you that one too. Is this the single one or the multiple one? This is the single one. So I'll just show it to you from this environment here. So here is the run, and here is the output. So let's go take a look at path lines again on this one, and you'll see it's pretty complicated. So here we are. So here's this is just, right here I'm just showing you the recirculation of the devices themselves. The chimneys have done a pretty good job getting the heat up out of there, but you see these low pressure areas keep pulling it back down, particularly as it comes over the edge of this fence. You see there's a low pressure right there, and these are being pulled right down into the intakes of the follow-on devices. And that's made worse by the generators. So here we have the generators down here. Let me show you one of those. This has got both in it, this particular plot. These are automatically generated, by the way, by the software. So here's both. Now, what's interesting about this, Kevin and I were looking at this yesterday as we were reviewing it. What's interesting about this one is that on the windward side, if you're a sailor, on the windward side, it's creeping into the intakes. So we have the exhaust coming off those stacks. By the way, these are high velocity. So the general heat coming off of the heat exchanger itself is not generally that bad. You have some of that. So this is temperature running, in the range of a couple hundred degrees Fahrenheit coming off there, 180, 200. These are running at like 900 Fahrenheit or 1,000 Fahrenheit, depending on the situation. I mean, fossil fuel burns at 900 degrees Fahrenheit on exhaust. It's typical 950, 980, sometimes 1,000, depending on the situation. And you see that exhaust is getting entrained into the intake of this chiller. Not a good thing. Under this wind condition, by the way, again, wind conditions will vary. What's interesting, however, is that as the wind passes over the building, you see less of it. There's a low pressure here, of course, caused by the wind going over the edge like this at high velocity. And then the wind slows down, which, of course, causes this to wrap down around and stay low. So downwind, so on the leeward side, it's not so bad. Kind of an interesting outcome. CFD will surprise you. The airflow will surprise you sometimes. It will turn out to be a case where you didn't expect that outcome. It's revealing in its analysis, and I have been, misled a few times, thinking up front that I know what that flow is going to look like, and then I make a run. I go, oh, of course, and there's why, or what have you. Okay, so, and then of course the most important is these inlet temperatures, right? Because that's really what you're after, is the inlet temperatures of those devices. That one is shown in this plot. This plot, again, takes a moment to load because there's so many little colored surfaces on it. But I'll show you that as soon as it loads. So here we have the outlet. Again, not too bad. We're seeing the ambient temperature of the wind here or the air is 110. We're seeing a 5 degrees rise. And let me just use my control keys here. That's a Y. N takes off perspective. So I flipped it around. The wind is actually now coming from this direction down. You can tell by the coloring. But you see that we're getting some infiltration into those chillers. I was showing you that earlier up here on the first set. Notice it's less on the second set. Kind of an interesting outcome. I wouldn't have predicted that necessarily. The wind is coming from this direction, so I'm getting recirculation on these devices. And it's always the most downwind one. It's this one that's got the worst situation. So it's seeing about a 5 degree rise in inlet temps down there. Still not too bad. So in this case, I would say under this run, I'd say, yeah, we're probably okay. This will probably be fine running it in this configuration. This isn't a customer's model or anything. It's just one I put together. It may not be necessarily indicative of the real world, but I thought it would be a good example to show you. And we were doing some testing and I laid this out. The runtime on this one, to do a model like this, runtime will be a couple hours to run that. But still fairly modest. If you're trying to do a number of variations, you can still get them done in a reasonable amount of time. So let me just go back to the presentation here and kind of summarize it and open it up for questions. We're about 10 minutes of right now. Again, if you've got questions, please write them in on the chat and Kevin will handle those for you and we'll get into a discussion a bit. But this kind of work is becoming more important. We have gotten pretty good at getting the data, the heat out of the room. For the past 10 years, 15 years, it's been how do we model the interior? And that's pretty well understood how to optimize the separation of hot and cold using containment, using fan walls, high density environments. We know just about how much you can get in terms of air. Liquid now as well, getting more. We're seeing a density of racks in the range of 50 kilowatts. We believe it's going to go to megawatt a rack or greater. Liquid's going to be a big part of that, getting it out. But that just means there's more of it outside. We don't have any liquid outside unless you put your data center in the ocean. And there is some of that, but it's kind of expensive. So if you're putting a data center on the Earth, you've got to dump it to the atmosphere. And dumping it to the atmosphere can be tricky. As that density rises, you need more area. Area is expensive. Real estate's expensive. So the density is going to go up. And the issue is, how do we optimize the placement and how do we ensure we have enough capacity to be able to handle the load given a prevailing wind condition or obstructions in the way or adjacent buildings or what have you. CFD is a great way to look at that. It separates truth from fiction. People will have an opinion. CFD allows you to prove whether or not it is going to be an issue. We say it's not parochial. It discourages bad ideas as well as encouraging good ideas. So with that, let's open it up. Kevin, do we have any questions at this point?
Yeah, so Gabriel has posted a few questions in the Q&A. One that he just recently posted was, as a rule of thumb, greater than how many air-cooled condenser fans and gens would we need to reach out to you for support to run these exterior models?
Well, CoolSim could go pretty big. I mean, I showed you one that's got, it depends how well you set it up. I mean, you can do a fairly complicated environment with, I mean, how many did I have in this last one? This last one ran pretty well. So, what do we got there? We've got 30 gensets. So you could do 50 gensets. We're not really limited by quantity. We're limited by lining them up correctly and getting that mesh set right. So you have to build it right, no gaps. You have to use cloning to make sure that there are no odd separations. It's all about the mesh. So in this particular one that I ran, we've got a mesh here of 9 million cells. That's not bad. 10 million cells on that. I think that was a rerun, by the way. I think that was a rerun of Post. That one's bigger than that. But take a look at the mesh. And so 10 million, 20 million, I've seen them run as high as 30 million without too much trouble. But you can see that's what the mesh looks like. We're putting cells on each one of those outlets. This is the hex mesh that I was referring to. I'm showing you just the surface. This is a volume mesh. If I showed you the whole volume, you wouldn't be able to see anything. So we're showing you just the surface, and you have to imagine that these things go off into 3-space. So for each one of these little cells I'm showing you here, it goes up as well into the volume, and you see a similar structure in the volume space. So 30, 50, 100, it doesn't really matter. And furthermore, if you run into problems, Gabe, we'll help you. In other words, one of my customers, what they do is they lay it out in CoolSim, and if it's too big, they can't get it to run, we pick it up in CoolSim and just take it into Fluent and run it for them by hand. Sometimes we charge them to do that, but not a lot. It's not a big number. We're not primarily a consulting shop, although we do quite a bit of that. We're a software development organization, but we know Fluent. So if you're having trouble, we will help you. And we provide essentially an extension to your design team. So in some cases, my customers lay them out and then we run them. And that's a relationship that we've gotten comfortable with doing. So
Another question that was posed earlier in the presentation was, I guess, about modeling the gens. Gabe was asking about that. And this would actually be helpful for me as well, because whenever I'm supporting jobs for CoolSim, I haven't really dealt with gens myself. And I know that you've shown in the presentation, but I would actually appreciate if you can kind of like go into it and see like how exactly you model a gen.
sure. I mean, a generator is really nothing more than a set of inlets and outlets with temperature and mass flow rate. So
So you
here,
just have the blocks and then,
this is just a block. Yeah, let me
yeah.
ungroup this. This is grouped at the moment. So let me ungroup this, and this is the stack coming out of the top of it. So let me just hide it for a moment. This is the outlet. So here's the outlet of the generator exhaust. Now you can get this spec from the genset. They'll tell you generally what the mass flow rate is. This one's running at 18,000. That's a pretty common number, and it's running at 1,000 degrees Fahrenheit on the exhaust. And the reason we haven't made these drag and drop kind of structure yet is because gensets tend to be very different depending on, how they're configured. I mean, they come in all different shapes and sizes. So it's easier just to create them by putting blocks in place, putting your inlet and outlet on it, because there's only one here, and then there'll generally be a couple others. So this one is the one that's pulling the air in. So this one is the air coming in. So this one's going to be in the range of 100,000, always, generally, depending on the size of the machine, but they'll generally run at 100,000. Temperature here, it's being dumped at 200 degrees. That's not uncommon, Fahrenheit, right? Because the water jacket's running at about 2. Even in your own automobile, look at the temperature of your automobile. They're running, the water jackets run 200, roughly 200 degrees. So yeah, that's what you're dumping at. Mass flow rate, based on the fan they've got in it, is set there. And so you stick that one there. And then the other one, which would be the inlet, you stick on the other side, and this one runs to atmosphere. It doesn't really matter. What you're trying to capture here is simply the amount of air going in. So this one's at 55 because I guess there was a couple other surfaces on this one. But this one's at 55, and you don't care about the amount of the temperature here because it's going to run ambient anyway. It's pulling in. This is the airflow is pulling in. And you can see that if I hide this block here, you'll see that arrow is facing in. So here's the air coming into the device. Here's the air going out of the device. That's for the heat exchanger. And then you've got a stack at the top dumping it to the atmosphere. That's the
Gotcha.
exhaust. Now, this would be true even if it was a gas turbine. Same thing. You would have an inlet coming in. A gas turbine would really only have 2 surfaces because the exhaust is mixed in the turbine into the output. So you would have air coming in one side, ambient like that, mass flow rate defined by the rotational velocity of the turbine, which is in the spec sheet. And on the other side, you'd have an outlet. And that outlet would be operating, fossil fuels is going to run about 1,000 degrees. This one's running at 1022. Sometimes I see them at 950, 1022. It's in that range. And you want to get the cross-sectional area correct because that's going to define the velocity, right? You've got the mass flow because the mass flow is defined by the manufacturer, so you'll know how much air is going through it. And then the velocity is going to be defined by the cross-sectional area down here. It's really all there is to it. You don't really care too much about what's going on inside that box. All you're worried about is the exhaust temperatures getting infiltrated into the adjacent equipment. So all you really
Right.
need
At
to
least
do
for
is,
us, yeah.
yeah, yeah. Now, some may want species too. They may, I've been asked, well, what about, toxic emission getting into intakes? Other places, CoolSim right now does not support scalar mixing. We could expose it. Certainly, we can do it in Fluent. Remember, Fluent runs behind CoolSim, so if you want to know what the percent of NOx or whatever your favorite gas is, we can model that using scalar mixing. So that's how you do it.
Thank you.
Mhm.
Looks like we have someone, JF, they just posted a question. Have you validated your results? For instance, if you were called in to solve an existing problem, have you tuned the model to match actual and then added chimneys or horizontal canopies and then run it again to predict how effective the solutions would be? Because
Yes.
I'm also curious about this as well, because like, oh, if you want to help avoid recirculation, like what are actually like the best ways to go about, whether it's like the chimneys or maybe even going away with those fences, as you say, seem to be more for cosmetic reasons rather than for practical.
The answer is if you have an existing situation, and I'll both internal and external, right? If your data center exists and you can build a representative model, always validate it. Always go in and make some measurements and tune the model to match the results. I mean, CoolSim's been around since the 1980s. I mean, it's got tremendous amount of validation on it. CFD can accurately represent, there's no question about this anymore, it can accurately represent physical phenomena to a high degree of accuracy. This is Fluent, this is running Fluent. The trick is making the measurement so that you can validate the model, because you have to make measurements. And I showed you the mesh earlier. You can imagine that what we do is a mesh. So we have this tremendous amount of data points that are created, and when you go in to measure something, the question becomes how many measurements are you going to take on the surface? So, for example, if I take an outlet of a chimney right here, you can see here I have three cells in this direction and three cells in that direction. I have 9 cells in there, so that would be 9 different points of integration is summarized and integrated over a surface. When you try to measure the exhaust temperature of a diesel gas engine, you probably, if you're lucky, using a probe and you're getting 1 point. So you have to be reasonable with your measurements in order to understand. But to answer the general question, yes, this technology maps very well to measure data. It has for, as long as the mesh is sufficiently dense, it will match quite well. And then you are going to do variations. The question was, what happens if I put a canopy in? What happens if I put a chimney in? Those are conditions that don't exist. Those are future conditions. You can't measure them because they haven't been built yet. Many of the cases we work on, the data center hasn't been built yet, or the exterior environment hasn't been built yet. So CFD is the best choice you have to try to predict the performance without simply guessing. I mean, you can guess at it. You can use rules of thumb, but CFD gives you an opportunity for higher fidelity representation that has been validated over 30 years in the automotive and aerospace industry. I mean, this is the same stuff they use on gas turbines, GE aircraft, GE, aerospace, and Pratt and Whitney were my customers, Boeing, my customer at Fluent. Validation of this stuff has been done over the past 30 years. It's sufficient, it's accurate, it's good enough to give you guidance about whether or not it makes sense to do something, like put chimneys on or put a canopy in place. And then you look at the cost of that and say, no, we can't afford to do that, or yes, that does make sense. It'll give you guidance. It is not a forensic tool. It's not going to give you temperature T because it models it differently than you measure it with a probe. What it will do, however, is give you a tool for using good engineering judgment. There's no substitute for good engineering judgment, but having a tool that allows you to model and predict behavior with a good degree of accuracy is a hell of a leg up over guessing. And it gives you a peace of mind that you've looked at that situation and the best science you have tells you this will or won't work. I mean, we kid about this. We spend a tremendous amount of computation and a tremendous amount of beautiful images output determining whether or not something will work, something that you can represent with a single bit. 1, it works, 0, it doesn't, right? However, what this does is give you more confidence about that decision. Will it work or won't it work? Is this worth it? This gives you a tool to analytically determine whether or not the case could or should be made.
Sounds good. Thank you for that. Gabriel also had like another question earlier, if this model could be shared.
Yes, absolutely. We can put this model up for people who are CoolSim. Gabe's a CoolSim user. Hi, Gabe. Yeah, we can make this model up. It's just an example model, but sure, we can make this available, no problem.
Sweet.
All right. Well, we're at the top of the hour. I tried to keep it to an hour. I want to thank everyone for attending. And we have recorded it. We'll try to post it. We have a YouTube channel if you'd like to take a look at some of the other work we're doing. We'll continue to do these if you find them useful. If you think there are topics, think of topics that you would like us to review, whether it's internal or external. Let us know. We also do a lot of consulting work, so sometimes it's not related to data centers. Sometimes we're looking at recirculation on hospital exhausts, for example, or we're looking at gas coming off swimming pools in indoor environments, or we're looking at manufacturing environments that are hot interior, and we're doing cooling modeling. We do a lot of different things in the built industry or the built market segment. We're generalists in CFD. However, we tend to hang around the engineering architecture segment, and we are specifically building tools for data center design optimization. So again, thanks everyone for attending. We look forward to having you come to another of our future events.